Hey everybody. Alright, so we're finishing Chapter 8 and we're going to jump into Chapter 9 in a second, which continues with some other different reactions and stuff. Alright, so first of all, let's review the last problem we did. It was a synthesis problem. I think we're on number 7 right now, so yeah, it's 7 was synthetic strategy. And this is the last problem we did. We'll do one more problem and then jump into Chapter 9. So what was our general strategy? We're trying to do this retrosynthesis thing where we go backwards. Rather than just focusing on the starting material and think, what can I do to that starting material to make the product? Alternatively, we think about, how can I make the product in a way that eventually leads me back to the starting material. That's kind of what we mean by retrosynthesis. And the process we use is called retrosynthetic analysis. So we're doing retrosynthetic analysis. So this is the last problem, and we're just going to do it again just to get back in the groove. Remember the strategy was, when we looked at that, we think about, how can we make aldehydes, and none of the reactions, the C-C bond forming reactions like Grignards and organolithiums, none of them make aldehydes. They make alcohols, but they don't make aldehydes. So what our strategy was realizing, you have to think through your little catalog of reactions in your brain, which is pretty small right now, but it's going to be huge before you know it, and think about what are the ways to make aldehydes. And right now you only know one way to make aldehyde, and it's through PCC, oxidation of a primary alcohol. So that was kind of how we started it. We're like, oh yeah, PCC, okay, and then we think, okay, there's the primary alcohol. And then we're thinking now, oh, we now have a way of attaching that primary alcohol. It's a CH2, right? A single carbon. So we can attach that single carbon to make the primary alcohol. We can do Grignard. And then we think, what are the different kinds of electrophiles in a Grignard reaction? And we think either ketones, which make tertiary alcohols, aldehydes, which make secondary alcohols, or formaldehyde, which makes a primary alcohol. And since that's a primary alcohol, we think, oh, it must be formaldehyde, right? So then we're like, okay, well, we're going to react with formaldehyde. And what's the Grignard going to look like? The Grignard is going to look like that, right? Like that thing with the Grignard right in the middle, right? Like, zoom in, right? It's that with a Grignard right in the middle, MGBR hanging off the middle carbon right there, right? And that would be this. And then we're like, how do we go work our way backward to Decolon? And then we can, go from add magnesium to the tertiary bromide, and then we can do selective tertiary radical bromination from Decolon, and that'll install the BR where we want, and then I'll put it right there. Of course, it could install it there, it could also install it there, but that's going to give us the same product, right? If it installs there, I flip it over and it's the same molecule as this, right? Okay, so that was a cool example. Let's do one more. This isn't that hard. I think we've pretty much covered all the sort of difficult situations, and we're going to get many more difficult situations as we go on through the course, but right now we're just trying to introduce this. Okay, so question mark. How are we going to do it? How are we going to do it? And we'll do this. By pH I mean benzene. I better just draw it out for you. pH though, that means benzene. Okay, so how are we going to convert this primary alcohol to this tertiary alcohol? And how many things does it look like we're adding? Well, it looks like we're adding 2. We're adding the bottom thing and the right thing, right? Maybe 2 squiggly lines. Alright. Those are our two squiggly lines. And it looks like if we have two squiggly lines, it might mean we have two different Grignard reactions, right? One to add one to add the other. And that's my first impression. I'm not going to go from the starting material, I'm going to work my way back from the product. Okay, seeing the product has a tertiary alcohol, that suggests I should be able to make it directly from a Grignard reaction. So we'll do a Grignard reaction going backwards. Which one do we want to add? The isopropyl or the benzene last? Well, it's your choice. I'm going to do the benzene last. So if I do the benzene last, that means the benzene will be a Grignard, benzene MgBr, and this would be correspond to the ketone, right? Those carbons would correspond to the ketone, right? So it would look like, the ketone would look like that. And the benzene, step 1, step 2, would be the Grignard. It says benzene MgBr. I'll do BrMg. Why do I do BrMg? Because I want to make it clear that the carbon is connected to the magnesium, right? It's not the carbon. The carbon's not connected to the Br. It's really carbon magnesium bromide. So I could either draw it this way, or I could draw it like the other way. MgBr. These are the same. I just drew them in opposite directions. All right. Okay. So now what do we do? How do we work our way from this thing way back to this? Well, we still have that one squiggly line. We still got to attach that. And just like in the last example, we don't have a magic way to install, like add a CC bond, like create a CC bond, and end with a ketone. Because all the Grignard and organolithium reactions that we know, your product's always an alcohol, right? Just like this was, you know, we reacted this with a ketone and we got an alcohol. So when I look at this, I'm like, I have to somehow add we have to add an isopropyl group. We still have to add an isopropyl group, but I can't do that in this next step going backwards, right? The next step going backwards cannot be the installation of the isopropyl group, because that reaction creates an alcohol, not a ketone, right? So the trick here is what? We had the same trick. Maybe it's the last problem, or I think it was the last problem, yeah. I think of like, oh, well, maybe this step is not the CC bond formation, it's the creation of the C double bond O, right, from an alcohol. Because right, here we go again. How many ways do you know that create a ketone? You don't know very many ways at all that make a ketone, like ways that that synthesize a ketone. The only way you know that makes a ketone is take an alcohol and oxidize it to a ketone. So imagine we have the alcohol. Now, secondary alcohol to the ketone, what's the reagent? Is it a hydride, or is it a chromium thing? Is it an oxidation? Is it a reduction? It looks like we're going from 1 bond oxygen to 2 bonds to oxygen, which is an oxidation, right? And so is it PCC or CrO3? What's the difference between PCC and CrO3 in terms of reactivity? Well, they don't care if it's secondary alcohol. They both work, right? The only time that PCC or CrO3 there's a difference is when it's a primary alcohol, right? If it was a primary alcohol, then PCC would make an aldehyde and CrO3 would make a carboxylic acid. But in the case of a secondary alcohol, as we discussed, it doesn't matter. I can use PCC or CrO3 acid, H3O+. It's all the same. Both of them are cool. Now we're kind of like we were in the initial part. Now we're ready to do the CC bond formation of the attachment of what? What do we need to attach? It looks like we need to attach the isopropyl group. So isopropyl Grignard from the aldehyde of that piece. Okay. So maybe I'll do, it'll be a step 1, step 2. So what are the 3 things I need? I need to draw the substrate, which is like going to be this thing. It's going to kind of look like that, right? But we're almost back to where we were starting. And then we need a 1 and a 2. What's a 2? 2 is always water. For now, assume 2 is almost always going to be water. Okay. So maybe we're going to attach, it's again a secondary alcohol, which implies Grignard addition to a ketone, aldehyde, or formaldehyde. Secondary alcohol will be from an aldehyde, right? And the aldehyde will kind of look like that. So that'll be the aldehyde, but with a double bond O. Alright, we're good. Now we just need that reagent number 1. It's going to be Grignard, right? What's the Grignard going to look like? How many carbons is the Grignard going to be? It's going to be 3 carbons. 1, 2, 3. 3 carbon Grignard, right? Aha! So now it's BRMG. There we go. And mechanisms, again, are not required in synthesis problems. I will never ask you, like, you know, here, propose a synthesis and tell me the mechanism. I'm never going to do that. You can add an arrow if it helps you to check your work, like there to there, to make the alcohol, you know, if you want. And if we want to do it over here, it would be that attack right there. But that's just to double check your work. I'm not going to ask you mechanisms in a synthesis problem. Okay, are we done yet? We're not done yet. We got to go all the way back to the starting material. So now we're like, oh boy, how are we going to go from that primary alcohol to the aldehyde? How do we do that? Because we're not done yet. We're almost done. How do we go from a primary alcohol to an aldehyde? Well, earlier we went from a secondary alcohol to a ketone using an oxidizing agent. This is just another oxidizing agent, and but in this case, it can't be CrO3. It's got to be PCC, because PCC gives you the partial oxidation, 1 bond to oxygen to 2 bonds to oxygen. CrO3 would give you the full oxidation, 1 bond to oxygen to 3 bonds to oxygen, like a carboxylic acid. So here's PCC. PCC, and it's DCM is our solvent. Not a really big deal, put in parentheses. And if you, on the quizzes and exams, forget DCM, it's okay. But when you read the book, you'll see, oh yeah, dichloromethane, DCM. It will mention that from time to time. Alright, so that was chapter 8. It was pretty fun. We're moving on to more and more kind of crazy chemistry and a lot of reactions and mechanisms, so be ready for them and take really good notes. Recopy your notes. All of those strategies will help. And index cards for the reactions, I think, is a good idea. So we're on chapter 9 now. Chapter 9, which is more reactions of alcohols. More reactions of alcohols and the chemistry of ethers. More reactions of alcohols and the chemistry of ethers. Alright, so firstly, some reactions of alcohols with a base. And we've already kind of previewed this earlier. First thing is that we can do quantitative deprotonation. Quantitative deprotonation. And all that means is, quantitative in this case means complete. Completely deprotonate. Rip off the proton. So use a super strong base. If we're using a base, it's got to be a strong base. So if the base is strong enough, if the base isn't strong enough, it doesn't work. So what are the strong bases? And we sometimes call them super bases. Super base. There's a couple of these super bases that we can use. One of them, and we'll just demonstrate with like methanol as our alcohol. Methanol, and one of the super bases is called LDA. It's lithium, diisopropyl, so those are isopropyl groups, right? Remember those? Isopropyl. It's lithium diisopropyl amide, which is kind of funny because lithium diisopropyl amide. Why is it funny? I think it's funny. It's funny because we've talked about amide before, and we always think of amide as like a C double bond O nitrogen thing, right? It's a carbonyl derivative. So this does not look like an amide the way you've learned amide, right? This looks just nitrogen with a negative charge. So this is a historical definition of the word amide. So it's anyway. So that's just different than the way you know amides. So this is an equilibrium, and I'm going to draw the equilibrium arrow in a second. Let's draw the products. H3C O minus, lithium plus. Okay, so that's like this is a base taking the proton, and then there's a electron pushing mechanism. Base takes proton, push it onto oxygen, and then you get the O minus. And then you get, over here you get H and isopropyl, right? And how do we know the direction of the equilibrium? Because I'm going to draw an equilibrium arrow in a second. We look at the what values? pKa's. pKa of the left acid is 15.5. pKa of the right acid, big number or small number? Huge number. It's about 40, I think. Okay, and so what's the rule? Do you go towards the small pK or towards the large pK? The answer is always to the large. So this is a very right-facing equilibrium. It goes far to the right, and K is roughly 10 to the, what's the difference of these? 25. Yeah, 25. K to the 25. So it's 1 followed by 25 zeros. 25, yeah, about 25, yes. And so it's very far to the right. And LDA, lithium diisopropyl amide, is one of these super bases. It just loves to rip off protons. Okay. Another one. Another way we can do this. Oh yeah, what's the name of the name of the thing with the O minus? These are called alkoxides. Alkoxide. It's like an alcohol with a proton missing, and then you have a metal salt on there, alkoxide. This specific one is also called methoxide. It might be called lithium methoxide. Lithium methoxide. Lithium methoxide. We've talked before about sodium methoxide and potassium methoxide. Okay, another one, another example. What's another way you could do this? Just use another superbase, like butyllithium. So butyllithium is just another like a Grignard almost, right? It's like almost like butyl Grignard. These are in addition to being really good nucleophiles, they're also insanely good bases. So this is also going to be to the right-facing equilibrium to make lithium salt of the alkoxide, and then butane. And how do we know the direction of the equilibrium, which I already gave to you? Of course, this is at 15.5 pKa. What's the pKa of butane? So you look it up in the chart. It's like 60, I think, right? 50. So now K is like 10 to the 35, right? So it's very far to the right. It's 1 followed by 35 zeros. So this is incredibly basic. Incredibly basic. It's a super base. We talked about, let's just do one more example. Another hydride reagent. None of these are hydride reagents. This is like a diisopropyl amide. This is a carbanion. But we did talk about hydrides as super bases, and we'll use KH. K plus, H minus. It's called potassium hydride. What was this thing called? This is butyllithium. Butyllithium. Okay, potassium hydride. We talked about the different kinds of hydrides last lecture, and like how, you know, NaBH4 is a nucleophilic hydride, and what else? We said lithium aluminum hydride is a nucleophilic hydride. But we also talked about, like, just if you have a metal like potassium hydride or sodium hydride, those are really good bases. So these are another class of super bases. So it's also going to be far to the right. K plus. So it's methoxide, K plus. Skipping all the lone pairs and stuff. And then you're getting H2 as your conjugate acid. Of course, that's a nice happy molecule. And pK is 38 of this. And this is again pK 15.5, like always. All right, so now we have like 3 bases we can use in order to rip off the proton of an alcohol and leave you with an alkoxide. So, all right. Okay. Another way the book mentions, this is A, quantitative deprotonation, if the base is strong enough. Another way that the book mentions is treatment with an alkali metal. Treatment with an alkali metal. So this is not an acid-base reaction, but it is a cool way, and the book mentions it, and it works well in the lab, so we do this in the lab. So in this case, like if I take, we'll say 2 equivalents of like butanol, and I throw in 2 Na dot. What's Na dot? Sodium dot. That's like Na metal. That's sodium metal, which is, I don't know if you've seen YouTube videos, you know, what happens if you drop sodium into water, but it's, the metal is especially reactive. This isn't the cation. This isn't like Na plus Cl minus. This is sodium metal, and it's exceptionally reactive as a metal, and when it reacts with water or alcohols, it's a redox reaction to form Na plus. So so when 2 alcohols react with 2 sodiums, you get 2 alkoxides, Na minus, Na plus. O minus, Na plus. And where do the H's go? How many H's were there? There's 2 of the molecules, so it's H2. So it forms a hydrogen gas. So you have to do this very carefully because there is heat developed, and so with the heat and the H2 it could catch on fire. So we often do this in an ice bath to kind of cool everything down and make sure it doesn't catch on fire. The mechanism is complicated. Mechanism, It's redox, and it's not a simple mechanism, and we're not going to present it or talk about it really. But this is just another way to do because you can see sodium is being oxidized to Na+, and then H is being reduced to H-. So the mechanism is kind of complicated, and these mechanisms are super easy. It's just the base takes the proton and then kicks the electrons off, right? We saw that mechanism like that. That mechanism is really easy, right? Acid-base reaction mechanism. This mechanism is complicated, but we'll see it in the class. In the lab, this is actually pretty easy to do. So if I have a little flask, I would not recommend you do it, but I've done it a lot. If I have a flask and I have like butanol in there, I can just drop little bits of sodium in there. And then maybe a little ice bath, so that the heat is dissipated. The other trick is you do this under, like you have a little needle with nitrogen atmosphere. So we blow out all the oxygen, because with oxygen, if you have oxygen around, then you have the potential for fire, right? Because when you drop the sodium bits in, you just drop little shavings of sodium metal, drop it in. It generates H2, but even H2 cannot catch on fire if there's no oxygen, right? Nitrogen, if I'm blowing nitrogen bubbles in here, like with a little syringe in a nitrogen tank, then it eliminates oxygen. Hydrogen will not catch on fire if there's no oxygen, right? So that's kind of a trick to how you do this actually in the laboratory. It's pretty cool, and it's fairly easy. You just drop in little sodium bits, and then all the oxygen proton gets converted to sodium plus, O-. All right. Alright, so we're still in number 1 for chapter 9, and reactions of alcohols with base. And why are these alkoxides, which just means a oxygen with a negative charge and a metal, why are they useful? Why would you want to make them? The answer is SN2 chemistry. We've talked about this briefly before, that you can do, activate an SN2 nucleophile by taking a proton off an alcohol. So let's just draw one example. We're going to go into detail later in the chapter. But if I have like this alcohol and I want to do an SN2 reaction on the OH and like attach something like a ethyl group or something, I don't know. Can I just do that? Can I just like throw in ethyl bromide or something? Answer is no, because that's not a good nucleophile, right? If I want to do SN2 chemistry, I need an SN2 nucleophile. That's not an SN2 nucleophile. So I might do like LDA, superbase, right? LDA is a superbase, and it gives me, I'm going to not show the mechanism. You could draw the mechanism. If I was drawing the mechanism, I'd first draw LDA out, which I'll do just for fun. Here's another way to draw it, kind of vertically like that, and then lithium plus, I'll do it for you. I'll do the mechanism. Alright, circle and pair, grab the proton. Alright, that's how you draw it. Remember, you don't show anything about the lithium going along. Like, I don't draw an arrow from O- to lithium or something. We just draw the lithium. We draw the lithium right next to the alkoxide. Okay, so, but then now we have a good SN2 nucleophile, and if I have a good SN2 electrophile, like iodoethane, and what's a good SN2 solvent? What are your good SN2 solvents? Like DMF or something, or DMSO, or maybe acetone. Acetone might do something bad here. DMF, DMSO, pretty good. and then SN2 reaction. Now you got your product, right? So why are these alkoxides useful? Is you can undergo SN2 reactions. We already gave this a name. It's the Williamson ether synthesis. It's later in the chapter. I just wanted to mention it again real quick. So we'll come back to that. Okay, so number 2. Reactions of alcohols with acid. Reacting with base. Why would you want to react them with acid? Because that can cause other reactions to occur. Alright? So, what happens if you react an alcohol with acid? Just in general. Example, alcohol, I don't know, H+, generic acid. What do you get? So the alcohol, in addition to being, it can be an acid itself and give away its proton, like we did up here. The alcohol gave away its proton and became an alkoxide. But if in the presence of strong acid, the alcohol can also be a base and itself get protonated, and you get something like this. And these things are called alkyl Oxonium intermediates. They're often used in mechanisms, so we'll like form this in the context of a mechanism. So what are a couple examples of this? So with a primary alcohol, this allows SN2 reaction in a way that like converts an alcohol into a halo alkane. So let me show it. This is for a primary alcohol. It's going to vary with different alcohols, different alcohol types. If I have like a primary alcohol and I react with HBr, it actually forms the alkyl bromide. You've never seen this before. It's a new reaction. It's not that complicated, but how does it work? And it's gonna. And the whole theme of this section right now is that we can protonate alcohols, right? We can protonate alcohols. So how could I protonate the alcohol for this to work? So HBr is a super strong acid, and when alcohol reacts with HBr, it gets protonated. Remember also back from the SN2 chapter that alcohol is a terrible leaving group. Remember that? It's not a leaving group at all. And what are the good leaving groups we know? Well, we know like Br is a good leaving group, iodine is a leaving group, tosylate, mesylate, triflate, chlorine, all of those are good leaving groups. But by this getting protonated, now we've actually made it into a good leaving group. So now we went from a bad leaving group to a good leaving group. So how, with this, whoa, I screwed up. Sorry, let's take a step back. There we go. Sorry about that. I'm glad I caught myself. Alright. Okay, so now we're cool. Oxygen attacks the proton, right? And now we have 2 protons on there. Okay, the Br is not there like I drew. That was a little mistake. Okay, so we're cool. So this thing is a good leaving group now. And what is the leaving group? Assuming it falls off, what is that molecule called? Have you ever seen that before? It's H2O. It's water. You're actually making water, and water is a very stable molecule. So that's why it's a good leaving group, right? So we have a good leaving group there. Alright, so now we have a good leaving group. Now we have Br minus. It's a good nucleophile. So we have a good nucleophile, we have a good leaving group. It's primary, which is a good SN2 substrate. So this goes and attacks and kicks it off. Okay? So that kicks off water, and then you get your product. So with a primary alcohol, we can actually convert the alcohol to a Br by SN2 reaction. So that's the second one is a little arrow. You can see that, right? That's from the bond. And it breaks off water. Water's the byproduct. So water. Okay, cool. Alright, so what else? Let's try another example. What if I have a double primary alcohol? And I treat it with HI. I'm going to assume excess, and usually you can always assume excess, meaning it's not just like one molecule of this to one molecule of that. It's excess. And I can convert the dialcohol to a diiodide. So that bond, let's be consistent. Doesn't really matter, but I'm going to draw the double bonds consistently. Yeah, there we go. Alright, so double primary alcohol to double iodide with HI. What's the mechanism? Of course, both oxygens get protonated by OH2 plus H2O plus. Alright, we cool with that? All I did is assumed each oxygen grabs a proton, kicks off an iodide, grabs a proton, kicks off an iodide. Now you have two good leaving groups, and I minus is just kick them off. 2 times SN2. Alright. Kick off those two good leaving groups, right? Cool. Okay, so with primary alcohols, you can convert them to haloalkanes, and it's an SN2 reaction. That's really important to remember, because with secondary and tertiary, it won't be SN2, it's going to be different. So let's show that next. Okay. So, from my last page, with primary alcohols, water's leaving group is an SN2 reaction. But with secondary and tertiary alcohols, water is also a leaving group, but it's actually more of an SN1 style reaction. And what always accompanies an SN1 reaction? Or E1 minor reaction. Okay, so that was the last page. Was primary is SN2, secondary and tertiary is going to be more of a SN1 E1 style reaction. So let's show an easy reaction first. Easy example. If I have a tertiary alcohol react with HBr, this actually makes the tertiary bromide and a little bit of the E1 minor byproduct. What's the mechanism of this reaction? This is a pretty easy mechanism. It's going to be the same kind of thing that we just did on the last slide. It just won't be SN2. So just use the alcohol to grab the proton, make a good leaving group on carbon. What's the charge on oxygen? Charge is positive, right? And now we have a good leaving group on a tertiary carbon, right? What's our good leaving group? H2O, good leaving group, right? Stable molecule. So water falls off. And now you get tertiary carbocation, and what is Br minus going to do to that? Maybe to give the product. What do you think? Br minus, use the plus. I'm just going to tack it from the bottom, just for clarity. And then of course, how do you form the E1 byproduct? That would be also from the carbocation. And maybe H and like H2O or something, or Br minus. Takes the proton, and then that would be the E1 minor byproduct. So for now, we always say, oh yeah, this is SN1, right? E1 is kind of accompanies SN1 reactions, right? Okay. Now, is there a way to do this that gives me primarily E1 product? Because we've always said, oh, E1 accompanies SN1. E1's always a minor byproduct, right? We always said that. So so we can actually do that. Example where we give more E1. E1 product. And the difference between giving more E1 product and like this, where it's like primarily SN1, is that to give more E1 product, rather than have a nucleophilic acid, because this is a nucleophilic acid, right? HBr it's an acid, and Br is a good nucleophile, right? And why did we get SN1 product? Is because we have a nucleophile, right? Br minus is a good nucleophile. How are we going to do this in a way that primarily gives E1 product? The answer is use a non-nucleophilic acid. So don't use HBr. Certain acids are not nucleophilic, and we'll show one. So to do a non-nucleophilic acid, the typical ones that we teach in this course are sulfuric acid, H2SO4, or phosphoric acid, H3PO4. Sulfuric acid and phosphoric acid do not have a good nucleophile, but they're insanely acidic. They're insanely acidic. And these ones, the primary product is going to be E1. Okay? And how is that going to work? What's the mechanism? Really easy. Protonate. Got a good leaving group. What's a good leaving group? Water. And what's going to happen to our good leaving group? On a tertiary carbon that loves carbocations, it's going to fall off and give us what? A carbocation. Maybe I'll draw it a little differently. Alright, we have a nice carbocation now. And how are we going to make this product? In this case, I can take any of these three, the protons off. Maybe I'll take the bottom one off so it sort of corresponds to this. But that's what E1 is, just forming an alkene. So let's take this proton and who's the base going to be? I usually just draw water, because you have, where'd water come from? Well, of course we made water, right? Water was synthesized right there, right? It was a leaving group. So we have water. Otherwise you could draw the conjugate base of sulfuric acid or the conjugate base of phosphoric acid. But it just takes the proton. Right, and then that forms the alkene product. Okay, so when we do this kind of stuff with a non-nucleophilic acid, and I spelled it funny there, it's non-nucleophilic acid, you get an E1 reaction predominantly. But if you do this same kind of thing with a nucleophilic acid, you get a SN1 product as your major product, with maybe a little bit of E1 as a minor byproduct. Okay. This is also true for secondary. So secondary is going to act like tertiary in terms of these mechanisms. All right. So for secondary, if I have a secondary alcohol and I react with HBr, it gives me the secondary bromide. Okay. What's the mechanism? Is it SN2 or SN1? Well, in this little section we're talking about SN1, so this is SN1. SN1. And if it's SN1, what kind of intermediate is it? It's a carbocation, right? Right. Carbocation intermediate. And what if I use a non-nucleophilic acid? HBr is a nucleophilic acid. I get SN1, carbocation. What are the non-nucleophilic acids? There's two of them. Something acid and something else acid. H2SO4, sulfuric acid, or phosphoric acid, H3PO4. H2SO4 or H3PO4. What kind of products do you get there? Not a bromide, it's actually E1. Also with the carbocation. And the product is an alkene, right? Okay, so as we showed, primary, water's a leaving group and it's SN2 style. Tertiary and secondary are water's leaving group and it's going to be SN1/E1. And this was a nice tertiary example, SN1, E1 minor byproduct with a non-nucleophilic acid, H2SO4 or H3PO4. We get a E1 predominantly through alkene, and that's because the conjugate base is not a good nucleophile for sulfate and phosphate. And then we also showed that for secondary, it's also the same kind of style, SN1 thing. And both of these are through a carbocation intermediate. You could draw the mechanisms for both of these. It should be pretty easy for you. Okay. All right. So, given how, depending on the alcohol, we can either cause like an SN2 style reaction or an SN1 style reaction. There's something cool that can happen, and I'm going to call this number 3, which is called carbocation rearrangement reactions. Carbocation rearrangement reactions. All right, so because remember for secondary and tertiary that we just saw with alcohols, and if we use like a nucleophilic acid or even a non-nucleophilic acid, they were carbocation. They were SN1 style. Maybe it might be E1 style, but in either case, it's carbocations, right? So, interestingly, because carbocations have different stability, right? We know this, that like primary is like really good, relatively speaking, compared to the other carbocations. Primary, or tertiary, tertiary, yeah. Tertiary carbocations are more stable than secondary, right? We know that. And those are like infinitely more stable than primary, and which are even more stable than methyl. But primary are so bad and unstable that they don't really occur anywhere. And needless to say, methyl carbocations are way too unstable also. But we do have these, like, cases where a tertiary carbocation is definitely more stable than secondary. And what we're going to see is sometimes a tertiary, or I mean a secondary, which is like a little less stable, can be converted to a tertiary or rearranged by a carbocation rearrangement reaction. All right. So, putting this all together, we say, therefore, there's a driving force. Thermodynamic driving force to generate more stable carbocations. Right? There's a driving force. And how does that work in maybe a reaction setting? So we're going to see there's two ways that you can do this to apply this driving force and to rearrange a carbocation. So two different rearrangement mechanisms. There's going to be two different ways to do this. The first one is called a hydride shift. A hydride shift. What's hydride? You ever hear that word before? Hydride. Where did we learn about hydride? Last chapter, remember that? Lithium aluminum hydride and sodium borohydride. What is hydride? That's H minus, H.dot minus. And so hydride shift is going to be kind of the shifting or movement of an H minus, H.dot minus. So what's an example of this? If we have this molecule, this secondary alcohol, and we react it with HBr, given what we just talked about how, alcohol gets a proton, maybe makes a carbocation, and then Br minus attacks, right? It's interesting that when that happens, the product is minor. That's weird. Is that weird? I think that's weird, right? I mean, you know the mechanism roughly, right? Oxygen's going to get the proton, become a good leaving group, fall off, plus charge, carbocation, right, and then Br minus attacks, but it's minor. And then somehow, through some weird mechanism, this is the major product. That is weird, right? We also have E1, I'm just going to ignore that for now. E1 is also minor. Let's skip the E1 discussion for this second, but because this is kind of SN1 chemistry, and E1 always accompanies SN1, but let's skip that for now. Alright, so how does this work? What's the first step of the mechanism? So we did this just now, just a second ago. So the oxygen is going to be a base and grab the proton and then liberate Br. And then what do we have? Oxocarbonium? or was Oxonium? I forgot what it's called. This is a protonated alcohol, right? Protonated alcohol, that's easy to say. We have a protonated alcohol. And then this, on a secondary, is it going to be SN2 style or SN1? As we said, just the last section, that on the secondary it is not SN2, it's going to be SN1. So that means carbocation, like, right? So now the oxygen jumps off. The leaving group falls off. Water falls off, right? And we get a secondary carbocation, right? So water goes away, H2O. And we have a secondary carbocation. But we just learned that something weird might happen because tertiary is so much more stable than secondary, that the secondary might rearrange in some manner to give a tertiary. And that's what's going to happen, and that's why we get a major product like this. Alright? So what happens now, I'm going to draw a Br minus attack, but I'm not going to show the arrow just because I need to, it's going to get complicated if I show this mechanism. There's another mechanism I want to show. But this is how this becomes that, right? Br minus attacks. Br minus attacks the carbocation. What I'm trying to show, though, is something called a hydride shift can occur, and that will explain the major product. Alright? So the other thing that can happen, in addition to Br minus attacking, is this hydrogen, the hydride, essentially, is a hydride that's attached to the, can jump. And I'm going to draw this just a little differently to make it more clear. Plus charge right there, yeah. Okay, so the hydrogen can jump to that carbon and take its electrons with it. So the hydrogen and its 2 electrons jumps. And that makes a different carbocation. So now the H is over here. Where's the plus charge now? Now it's there. Aha! Now what's Br minus going to do? Now it attacks the carbocation, and then you're done. So that explains how this major product can form. That looks a little different than what we started with, because now the Br is on the tertiary position. Alright? That's cool. Alright, so then the mechanism of this, I mean, I showed the nice mechanism, but there's a mechanism in the book that I'll show on my slide. Is figure 9.2 of how the hydrogen actually shifts, this hydride shift. Alright, so this is on the chapter 9 stuff on the website. I gotta post the chapter 11 stuff next. We're skipping chapter 10. But for chapter 9 we go to the little PowerPoint thingy, and here we are, and it's the further reactions of alcohols and chemistry of ethers, and these are supporting slides for the mostly whiteboard presentation. So I always print these out and put them in your notes or whatever. Anyway, what this is showing is kind of how that works, the hydride shift, like a mechanism for how it actually happens. Mechanism for carbocation rearrangements, hydride shift reaction that we're talking about. So this shows kind of where we start. So we have a secondary carbocation, there's kind of a hydrogen next door, and secondary carbocation is not super stable. It would be happier if it's a tertiary carbocation, and so what happens is the hydride just jumps, it migrates, so it just sort of swings over kind of to the right, and now it's kind of in between and sort of bridged between the two carbons, and now rather than one carbon be completely positive, now both carbons are delta positive. So it's like a transition state, right? And then in the end, the hydrogen's completely jumped over, and now we have a tertiary carbocation, which is nice and stable. Okay. This kind of just shows another way to draw that. Remember that concept of hyperconjugation, of how carbocations are stabilized, how you know, the lone pair, sorry, the bonding electrons on the CH are kind of overlapping with the partially positive, with the carbocation, right? And how if you have a bunch of these, it stabilizes carbocations. But a secondary doesn't have that many of those stabilizing interactions. Anyway, through hyperconjugation, that kind of shows how the hydrogen can migrate and just sort of just jump over, and so it's bridged in this sort of transition state, and then in the end it's completely on the other carbon, and you went from a secondary carbocation to a tertiary carbocation, which is more stable. And of course, the tertiary carbocation is stabilized by hyperconjugation itself. So that just kind of shows mechanistically how this hydride shift stuff happens, which is pretty cool. Okay, so another thing about hydride shifts is they typically go from like a secondary to a tertiary. Why would it do that? Carbocation, secondary carbocation to tertiary. Well, the reason, of course, is because secondary is a little less stable and tertiary is a little more stable, right? That's why. But sometimes they occasionally go from like secondary to secondary, which are equal in energy, right? This makes sense. Secondary to tertiary is like, oh yeah, less happy, more happy. Occasionally it'll go from secondary to secondary, which is like equal in happiness, right? Or it might occasionally go from tertiary to tertiary. And we'll show these examples, and the textbook has a couple homework problems of like, oh, secondary to secondary, tertiary to tertiary. But what will never happen, never go from an unhappy one, I'm sorry, a happy one to an unhappy one, right? It'll never go from like tertiary to secondary. That does not make sense that it would ever do that. Exclamation point, exclamation point. You would never go from a happy molecule to an unhappy molecule, okay? So it's usually going to be secondary to tertiary, occasionally secondary secondary, or occasionally tertiary to tertiary. So those are the types of hydride shifts that might happen. Let's show a couple more examples now. Alright, so we're on hydride shift still. Hydride shift. Okay, so let's see. Let's show a mechanism for this secondary alcohol react with HBr to make that, which is it totally makes sense. It's just a SN1, and also that. So it'll make a mixture of these two products. How's that going to work out? Well, of course, this is SN1 with no shift, no hydride shift. This is an SN1 with a hydride shift. H shift means hydride shift. Okay, you should be able to draw the mechanism for these. Why don't you try it? You come to office hours if you need help on this. But essentially, hydrogen grabs the proton, make a good leaving group. Leaving group goes away, and then Br minus attacks to make this product. or you hydride shift from like the central carbon to that carbon, right? Just H shift, and you make a new carbocation, and then that gives you that product. So that's actually pretty straightforward. I'm not going to show the mechanism, but you can try it. What about this tertiary alcohol, HBr, would potentially make that tertiary bromide. And this tertiary bromide. Of course, same exact thing as this problem. This is no shift. This is yes shift. Okay. So same exact thing. Oxygen grabs the proton, makes a leaving group, right? Oxygen grabs a proton, makes a good leaving group. Leaving group falls off, and you make it one carbocation there, and then the Br can attack, or it can shift to make the second carbocation. I'll just draw the carbocations, but you should draw mechanisms to form those carbocations, right? So you can complete the full mechanism to how this all happens. Essentially, though, all you have to do is show the hydride shift from there, and you know that maybe I'll help with just that step. How does the hydride shift work? H, and then circle the H, and that's the shift, and that transforms one tertiary carbocation into another. And why does that happen? It's because you're going from two energetically equal things, and they can kind of transition back and forth, right? Okay, so there we go. HBr. Is HBr a nucleophilic acid or a non-nucleophilic acid? And of course it's nucleophilic, and that's why we're getting these nucleophilic reactions, right? Nucleophilic, nucleophilic. What's the non-nucleophilic acid that we're talking about? Because this can also occur with non-nucleophilic acid. What is our non-nucleophilic acid from this chapter? It was the H2SO4 or H3PO4. And what was the reaction that occurs with a non-nucleophilic acid? Not SN1, but what's the reaction? It's E1. So let's show that. Secondary alcohol. Sorry, my bad. Let's fix that. Secondary alcohol. H2SO4. Wow, that's weird, huh? It formed an alkene, but at a different place. So how did that happen? And again, this is either sulfuric acid or phosphoric acid. Alright, and it's sulfuric acid or phosphoric acid. And what's the mechanism for how this forms? Usually I make the students just do this, but I'll help you out this time. These kind of things could be quiz questions. So I look at some of the homework problems. First we make a good leaving group. First you make a good leaving group, and then what happens to the leaving group? It goes away. and water goes away. And what are we left with? When water goes away, we have a carbocation. How do we get from here to there, though? Because the E1 reaction is like a neighboring proton that gets taken off. And what are we doing now? We're doing hydride shifts. So why don't we go from a secondary to a secondary, and then that gets us closer to this alkene, and that's what we have to do. So just do a hydride shift. Draw the, so we're going to go from a secondary to a secondary. So the H, how do I do it? I circle it and jump. And what does that give me? The hydrogen migrates. What do I have now? A new carbocation. A new carbocation, alright? And how do we finish this off? Now remember the E1 reaction is just you just take off a proton next to a carbocation. So just take this proton off. Maybe H2O sits around. Okay, and how does that form the alkene? Take the proton and do what? And you form the alkene. That's all there is to it. And then that forms the final product. That was a pretty cool problem. And that uses a non-nucleophilic acid, so it does not do SN1, it just does E1. Okay? Alright, so I'm going to end, but I just want to mention there's another kind of carbocation rearrangement. This will be, it's called Alkyl Shift instead of Hydride Shift. And this one will be on the next quiz. So Hydride Shift will be on the upcoming quiz, and then this will be on the next quiz. I'm going to draw it real quick just to show you what it is, but it's just a slightly different kind of rearrangement. So I'm just going to cut to the chase and just draw what happens. Oops. This is it in a nutshell. It's called Alkyl Shift instead of Hydride Shift. I'll definitely go over this in detail next time, but it's the same thing. Protonate, leaving group, goes away. And now instead of a hydride jumping, it's an alkyl group, like a methyl. So okay, something like that. And then that gives you a new carbocation. Br minus tax. Okay, so yeah, this is kind of where we're going next, and it's not going to be on this quiz. Hydride Shift will be on this quiz. This will be on the following quiz. All right, so we'll go over this one in a little bit more detail next time.